Hello everybody and welcome to this mini-series about rocket turbopumps. My name is Patrick from the NUMECA Cadence office in Germany, and in the next 3 videos we will build or design this rocket turbopump right here, which is running on liquid methane, and we will go all the way from the 1D meanline design in PUMPAL. So we will have 3 stages, beginning with a high solidity pump followed by 2 low solidity pumps. We will then switch to accent, where we will build our final 3D geometry, followed by a detailed 3D CFD analysis in Omnis. To give you a brief heads up on the boundary conditions, as I already mentioned, we will be using liquid methane. And we will start with about 20 bars and 135 Kelvin, which brings us quite close to the liquid saturation line right here. And we will increase the pressure to approximately 600 bars. We see the isentropic process right here. And the solid line basically shows approximately the state of change we will be seeing in the CFD. Right, so I would say we begin with PUMPAL. I hope you enjoy this mini-series. Please give us feedback, and if you have any questions, don't hesitate to contact us. So let's get started. So as usual, we will start with the preliminary sizing in the meanline tool, that is PUMPAL in our case. We want a single stage, and we will apply the metric SI unit system. In our case, since we will start with the inducer, we are selecting the wizard for the high solidity pump. And basically the first real information PUMPAL needs are the upstream conditions as the first step, and the second step, of course, we will have to define a fluid. So all mainline tools offer a variety of fluids and also specific heat polynomials or NIST libraries for each fluid. The total pressure rise in our case will be 20 bars, and we will have to apply some geometric values, all of which we will be able to change later during the design. So we're going to apply some angles here, then we come to the vanless diffuser, and then we already reached the end of designing designing the first stage. So as a quick reminder, if you want to change properties at certain locations, you just double click there, for instance, the inlet of the impeller or the exit of the impeller, you just double click, and then you get all the properties that you want. Now the first thing we're going to do here is we want to check how the radius ratio at the inlet influences our performance. And for that we will use the design helper, a tool which we already introduced, I think in one of our first life hacks on this topic. So we would like to increase the total dynamic head by changing the radius ratio from 0.3 to 0.5 in a certain increment. And then the design helper iterates over all these designs and evaluates them. And then we will be able to post-process. So as you can see, our total dynamic head increases as the radius ratio increases. However, for instance, if we take a look at the total efficiency, we see a different trend. So in our case, I basically decided to stick with some middle ground here and chose a radius ratio of 0.4 at the inlet. Now, a different way to iterate like this is to do it manually, and we will apply this method to changing the exit of the impeller. And to do that, we first select autosolve and then accumulate designs. You will see in a minute why, because now if we change the radius ratio at the exit, the solver runs automatically. and PUMPAL keeps in mind the previous runs. So now, since we have changed the radius ratio at the exit, now we can take a look in the table and see how the values, for instance, total efficiency or total dynamic head have changed by changing the exit ratio. Yeah, so here we have basically all the values that are relevant for us. We can just split the view vertical and then do our analysis right here. As a next step, you are of course also always able to take a look at the velocity triangles at the impeller inlet or the outlet, and you can also switch between the primary and the secondary zone, which will contain all the losses. And that's pretty much it for the design mode and the preliminary sizing. Next, we will switch to the analysis mode, in which we can take a look at our performance map and do some additional changes. So the first thing we will do is we will switch to multiple data, which will allow you to calculate a speed line and take a look at your QH curve. All you have to do is run the solver and then use a default layout. And this will bring up a window showing you the efficiency, total dynamic head, and the power, and whatever properties you feel are relevant to you. Of course, you will also be able to save these points in a separate file, so you will be able to compare it later after you did some changes to your design. And yeah, so that will be running under the overlay function. Right. So next we will do some manual changes to our design at the inlet and the outlet. That's mostly related because, or the idea is to reduce a little the size of the inducer in order to match the low solidity pump a little bit better to the stage. So we'll just run the solver here after we did our changes. Get back to our performance map, and now we will be able to overlay our previously saved map. We just have to select the saved file, and then we will be able to compare the designs. So now we are finished with the inducer or the high solidity pump. We will now add the second stage after switching to single data again. And we will add the second stage by using add stage new. Later we will also clone this, but right now we will create a new stage, and we can set it up in the same way. All we have to do is click on it, switch to design, and then tell it that we will want to use the wizard. And basically we keep most of the settings equal. I think, yeah, all we have to change is the angle reference. That's just a matter of taste. And of course, switch to the template for the low solidity pump. The fluid and the upstream conditions remain the same. All we do is we increase the total pressure rise, which will be 20 bars in our case. We have to apply, or we have to give a first estimate for the radius ratio, which will probably not fit at the beginning, but we can change these values later when we come to the analysis mode again. And most of what we see here is pretty much self-explanatory. We'll increase the number of blades. So the wizard really helps. It keeps things simple, and it's quite intuitive. Here we can define seal options. Note that if you do not apply any values here, PUMPAL will apply default values for you. Next, we have to define some back sweep, some modeling parameters, and then we get to the diffuser. We will apply a simple diffuser with a pinch here, so no manned diffuser as of yet. All it needs here are some radius ratios and the width of your diffuser. And since So we have multiple options here. You can apply a volute or a collector, but in our case, since we will add a third stage to this second stage, we have to apply a return channel. And PUMPAL, of course, also needs a few geometrical values in order to design this channel, all of which you will also be able to change later on. And that's it for the second stage. So I will just save this again right here. And after solving the stage, we get this new assembly. Now, as you can see, that looks quite well. The last thing I will do is I will apply some minor changes to the exit of our impeller. That is something you will have to do a little with experience. Usually the values PUMPAL comes up with are quite well. I'm just gonna apply some minor changes here. And we just rerun the solver. Next, we can take a brief look at our performance map. So the performance map can be viewed individually for each stage, so the inducer or the low solidity pump, or you can also go to Window, Multi-Stage, Map View, which will show you the performance for both stages combined, or you can also use the option to use the multi-stage table view, which will also give you an overview of the most important parameters. Now, if you want a quick update or if you want to take a brief look at your 3D design, you can always use the Agile link and send this design to Accent and take a look there. So as you can see, this is what we created so far, filled with some estimates from Accent to go from the 1D design to a preliminary 3D detailed design. Now, as you can see, I have applied some additional changes to the design we did so far. Next, we will clone the second stage, which is a very nice feature because, as you can see, it takes all values from the first stage and transfers it directly to the second stage, which may make your life a little bit easier. All we have to do now is, in this case, I would like a vaneless inlet upstream of the third stage. Actually, that's something I would probably also do upstream of the inducer. It's actually really not a big problem. All you do is you go to Layout and select a vaneless inlet. The last thing we have to do here is to change the exit conditions from a return channel to a volute, since we will not be adding any more stages at this point. And you can also do that via the layout and change the exit element from return channel to the volute. And to get an estimate of the sizing of the volute, you have to switch from analysis to design mode here, because the entire design itself is already in analysis mode, and to get the preliminary sizing you always need the design mode. So I'm gonna select an overhung volute here, and then I will say how big the volute is going to be as a percentage at the smallest section, and I will apply a radius ratio here. All of these parameters, you will also be able to find that in the user guide. And as soon as you've done that, you rerun the solver, and then we are finished with our design right here, including 3 stages and a volute. Now, I agree this is quite a lot. I just wanted to really show you how you could set up multiple stages with a volute right here, because this is something you find quite often in rocket turbo pumps. So I did some further minor changes to this design before I sent it to Accent. Those changes basically include, for instance, a vent diffuser, which is something you can add also very easily via the layout function. All you have to do is you double click on your vanless inlet and add multiple segments to your diffuser, and then select what type of diffuser you want. The same goes for the geometrical parameters for this diffuser. And that's pretty much all there is. This is exactly the point where we will start in the next video. So we will transfer this design to Accent and then apply some additional minor changes, followed by a complete setup of this design later in Omnis. I hope you enjoyed it so far. I know it was quite a lot. I promise the next 2 videos will be not as dense as this one. So I see you then.